Step right up, ladies and gentlemen. What we've got here is a circuit smorgasbord, an electronic buffet, an all you can eat AC to DC extravaganza. We've got a lovely selection of non isolated AC to DC buck converters. We've also got some AC to DC flyback converters with built in MOSFETs, and some lovely built in silicon MOSFETs with AC to DC converters as well. Yes, my friends, we're talking all about AC to DC controllers and converter ICs today. You better grab a plate, because we're digging in. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Mitch Van Ochten from ROHM Semiconductor and I explore the what, where, and how of AC to DC controllers and converter ICs. We investigate the benefits of ROHM's non-isolated AC to DC buck converters, AC to DC control ICs, and AC to DC flyback converters, and how you can utilize these solutions in your next design. And before we get started, don't forget to click that link. There you can find even more information about this topic from ROHM Semiconductor. Hi, Mitch. Thank you so much for joining me.
Well, thank you, Amelia. It's good to be here.
Excellent. Okay, so we're talking about AC to DC today, but before we dig into the details, Mitch, what all will we be covering?
Well, today, Amelia, we're going to talk about our non-isolated AC to DC converters. We're going to talk about parts that have a built-in MOSFET, parts that have a built-in silicon carbide MOSFET, the quasi-resonant controllers, and power factor correction IC.
Excellent. Okay, so let's talk about that first bullet point you mentioned, non-isolated AC to DC.
So to begin with, I think we'll talk about our BM2PXX family. These parts are of a very compact size parts, and they have either 65 kilohertz or 100 kilohertz switching frequency, and they have either a SOP8 package or a DIP 7 pin package, whichever you prefer. We also have variations with adjustable output voltage and adjustable current sense as well. The nice thing about these parts is that you end up with a total component parts count that is very small. Roughly 8 parts, including the chip itself, can get you a non-isolated AC to DC conversion.
Okay, so Mitch, what kind of solutions does ROHM offer for a non-isolated buck converter?
We have parts that range in current from about 300 milliamps to about 2 amps, and they're rated for temperature range of minus 40 C to 105 degrees C. And the majority of the parts are rated for a drain voltage up to 730 volts and an output voltage that ranges anywhere from 8 volts to 32 volts. So the next slide shows a picture of the evaluation board for the BM2PXXX family. We have some curves that show output power versus efficiency, and we show load regulation, that is output voltage versus output current. So the nature of these very simple parts is that at very light load currents, they do tend to have an increase in the output voltage. If that is a problem for your application, there is a way to add an opto-isolator for feedback to improve that load regulation.
Okay, so Mitch, what kind of output voltage options does this solution come in?
Okay, for evaluation boards for this solution, Amelia, we have voltages ranging from 10 volts all the way up to 24 volts. There's 7 or 8 various voltage ranges that are already stuffed with the proper resistor to get the output voltage that you're looking for. And these simple eval boards are set up for 150 milliamps of output current with a peak current limit of 450 milliamps typical. And they can be used for either a positive supply or a negative supply. Keep in mind they are non-isolated. 7 just gives specific part numbers for the particular voltage that you might be after, and also a choice of 3 different output currents, either 300 milliamps, 500 milliamps, or 700 milliamps.
Okay, so Mitch, ROHM has a new lineup of this series, right? Can you give me some details about that?
Yes, this would be our BM2QH series. This series features a quasi-resonant controller, which helps with reducing EMI. It also includes a built-in 900 volt MOSFET for some higher voltage applications. And it comes in 2 different strengths, if you will. MOSFET, which is RDS on of 6.4 ohms or 12.9 ohms. These parts are able to accomplish regulation without the need for optocoupler or shunt regulator, like many of our AC to DC parts require. So, because they have this ability to sense a secondary winding from the transformer, they eliminate the need for that optocoupler. And the 2 different RDS-RON ranges end up getting you power supplies that can be on the order of 15 watts or 8 watts. Here's a little additional detail on how we are sampling that feedback winding in order to accomplish the regulation. So it's a direct auxiliary wire sensing, and you can tune the output voltage with a single resistor. We also have a feature that can help eliminate the effects of the forward voltage across the diode to help improve the load regulation.
Now, what about a solution with no opto isolator? ROHM has a new solution here as well, right?
Yes, that's correct. As we have been talking about, and we can see in the schematic diagram here, in fact, there is no opto and there is no shunt regulator that's commonly associated with the use of the opto isolator. So we think that will help reduce the overall cost, the overall parts count for this particular AC DC solution. And the 900 volt rating for the MOSFET will allow its application in higher AC input voltages than what we typically could handle in the past. The quasi-resonant operation ends up giving lower EMI than systems that are not quasi-regulating. We also have an AC sensing in these parts that can detect a brownout and help prevent operation during a brownout. And the overcurrent sensing is also related to the AC input voltage. So it's dynamic, and at higher input voltages, the current limit goes down.
So, Mitch, will ROHM be offering an integrated GaN solution for AC to DC?
Yes, I'm glad you asked that, Amelia. We do have samples available now for our BM3GQ1 family. It is an integrated gate driver and GaN solution, and it also has integrated current sensing. So you do not need an additional external current sense resistor. This is a 650 volt rating for this particular GaN product, and it is a quasi-resonant type of converter. As we mentioned before, this results in lower EMI than some of the other types of controlling solutions. We also have on this part an under voltage lockout, and we have the X capacitor discharge function, which we'll talk more about later, but that's basically a system that guarantees that on a plug connected supply, when you pull the plug out of the wall, if you should inadvertently touch the prongs of the AC plug, that prevents you from getting a shock. So this part can operate with power supply input voltage to the IC itself, anywhere from 6.9 up to 55 volts. And the GaN itself, the GaN device has a on resistance of 150 milliohms.
So, Mitch, what would a block diagram look like here?
So here we have the block diagram of the complete system, the AC input filter, the bridge rectifier, the diodes that are used for the X capacitor discharge function, and so on. And we also show the secondary rectifier. This particular GaN solution does require the opto-isolator for feedback, but it has the advantage of a small 8 by 8 millimeter package and up to as much as 65 watts coming from a very small package. It's appropriate for chargers and things like that. That would be self contained and plugged directly into the wall.
Mitch, what if I need a high efficiency at light load? What kind of solution would you recommend here?
For the highest efficiency at light loads, we have our BM2P XX family. These parts are available with three different choices of MOSFET on resistance: zero point 0.7, 1.0, or 3.0 ohms. And they run at a frequency of 65 kilohertz typical. And they have also the X capacitor discharge feature that we talked about before. And they have a dynamic current limit where the amount of current limit is related to the amount of incoming AC voltage. And they also include a jitter on the operating frequency. So, in other words, even though the nominal frequency is 65 kilohertz, we have a dithering function that raises and lowers that switching frequency to spread the EMI over a wide range of frequencies and makes it easier to pass the emissions regulations. And this does also include the brownout function to stop operation if the AC input does get too low. We've used a feature of this package where we actually allow 8 pins to tie to a copper heatsink on your board. And with that solution, you can get as much as 45 watts of output power with this part.
So, Mitch, talk to me a bit about the built in X cap discharge element of this solution.
Sure. So the safety standard related to this X-cap discharge says basically that when the user pulls the plug from the wall, that within 2 seconds, the voltage across the prongs needs to be below 60 volts. So that's sort of considered the threshold for getting a shock. Without this X-cap discharge feature, when you pull the plug out of the wall, there could be as much as 130 or so volts remaining on that plug from some of the capacitors inside the supply that are used to reduce EMI. Those are referred to as X capacitors because they are connected across the line to neutral on the AC input. And those caps could potentially hold a charge for several minutes. So having the ability to get rid of that charge within 2 seconds or less is a good feature and needed to meet that particular IEC 62368 safety standard.
So, Mitch, earlier you mentioned AC to DC flyback converters as well. So, let's talk about those.
Okay, in this chart we have a X and Y axis showing the output power versus the particular package size, and we have a choice of surface mount devices or through hole devices. And also we have through hole packages in the TO220 size, and the amount of power those can deliver depends on whether you've got an external heatsink attached to the package or not. But we're talking power ranges, Amelia, ranging from 10 watts up to more than 70 watts with the family of AC to DC flybacks.
So, can you talk to me a bit about those two different types of flybacks?
Yes, ROHM separates the flyback family into what we call type 1 and type 2 flyback. The type 1 is the simpler type, and it does not include that X capacitor discharge that we talked about earlier. the type 1 is power levels of 30 watts or less, whereas the type 2 has the X cap discharge. It also has lower standby power if that's important in your application. And it comes in output powers up to as much as 45 watts.
So, talk to me about the solutions that ROHM offers here.
For our BM2P 06 or 10 or 13, I call that our standard flyback IC. The chip itself is going to run off of a secondary winding that's from 8.9 to 32 volts. These parts include a MOSFET that's rated for 730 volts, and they also come with an RDS on of either 1 ohm or 3 ohm, and in a DIP 7 type package, or some of them also come in the SOP 8 type package. They're available at 3 different switching frequencies: 65 kilohertz, 100 kilohertz, or 130 kilohertz.
So, talk to me about the light load, high efficiency aspect of this solution.
So, with these particular parts, there are two things that we do to achieve high efficiency at light load. First of all, you have the ability with an external resistor to determine what the minimum on time is going to be for your MOSFET. Secondly, we have a burst voltage setting function. So, what happens is as the load gets lighter and lighter, the part does not actually need to run continuously to support the load. So, it can run for a burst of 4 or 5 cycles and then stop running. And then as the voltage on the load starts to decay, it begins to run again. So by running in this burst mode, the efficiency can be substantially increased. Without those two features of the on time control and the burst control, at light loads, the efficiency might fall to 75% or something along those lines. And with those features, typically you can get efficiency at light load of more like 80 to 83%. On this slide, we have a complete lineup of all of the AC to DC converters that do have built-in MOSFETs, and we're talking everything from 650 volt rating all the way up to 1700 volt ratings, and it also has on the y-axis the available output power. So we're talking about chips with as low as 8 watts output power all the way up to 100 watts of output power. So a very broad solution of AC to DC flybacks.
Okay, so let's dig into the details of ROHM's built in silicon carbide MOSFET AC to DC converters. What kind of applications are we looking at for this solution?
Many times in industrial applications, and I'll say that applications related to industrial three phase, 480 volts AC input, that sort of an input is very popular these days for high speed electric vehicle charging. And it's also very popular for welders and things like that, induction heating and things like that. So, whenever you've got a product that's requiring this three phase 480, it's common to need 24 volts DC for what I would call housekeeping functions. For example, running small fans to keep the parts cool, running indicator lights to let the user know what is the status of what's going on, running small switches to turn things on and off. All those type of things require a low voltage DC supply of 24 volts. And the nice thing about the converters we're talking about now is that with that 1700 volt built in MOSFET, with just a simple bridge type rectifier off your 480 volts AC, you can make a flyback supply that will get you 24 volts at somewhere between 25 and 40 watts of power.
So, can you talk about the silicon carbide MOSFET solution applied power a bit more?
Sure. So we have this solution available in a surface mount package, a TO263, which takes advantage of the copper on the top side of your board for heat sinking. Or we have it available in more like the TO220 with a hole for mounting. And that can also be then attached to an external heat sink. So depending on the size of the heat sink you choose, you can get potentially more than 100 watts of power from this type of a solution. The surface mount version, the TO263 with copper side of the PC board for heatsink, you can get up to 48 watts of power.
So, what does the lineup for this solution look like?
Here we have a little more detailed picture of the parts themselves. The parts come with a protection from overvoltage that can either latch up until the incoming voltage is removed, or it can do an automatic restart where it repeatedly tries to operate and then decides after each try whether or not the input voltage is within acceptable ranges. And for overload conditions, the same thing is true. We have parts that will do an automatic restart. And if, let's say, you've had a brief momentary short circuit, so the part will shut down to protect itself. But then the next time it tries to restart on its own, if the short circuit is gone, it will be back to normal operation. The other choice is if it ever does detect an overload, it will latch into the off state and stay there until you disconnect the primary power.
So, talk to me about the quasi resonant control as well.
With the flyback style of power supplies, the more traditional way of operating and the simpler way of operating is to provide a pulse to the power device at a specific frequency and to really not pay attention to how much voltage is across the device or how much current is going through it. So that tends to create quite a bit of EMI when you switch with a large voltage across the power device. With quasi resonant, what we do is we monitor, let's say, the drain voltage for that power MOSFET that's in the product, and we observe what is called a ringing on the drain voltage that happens when you shut off the switch and the energy's been sent to the secondary. So that ring actually crosses 0 volts at one point on its way down. So with quasi-resonant, what we do is when that crosses the 0 volt point, that's when we again turn on the power device to get energy stored in the flyback transformer. So by switching when the voltage is close to 0, you greatly reduce the problems with EMI and radiated energy that is often a headache to deal with.
So, ROHM offers a D2 pack of this 1700 silicon carbide MOSFET as well, right?
Yes, that's correct. That's the surface mount version that we talked about briefly. And this part can pick up its heatsink just from the copper that's on the top of the circuit board. And this part does have a number of nice features. It's got the quasi-resonant control that we spoke about for low EMI. At light loads, it's got the burst mode for a better efficiency. And it's also got overcurrent protection on a per cycle basis. It has a soft start function, and it's got the brownout protection for under voltage lockout. And with that 1700 volt rating for the silicon carbide inside, it's able to handle your toughest industrial applications.
So, creepage and clearance are important design concerns to keep in mind. How does this solution stack up in those cases?
So this part has an increased distance for the creepage and clearance, and we have the picture that illustrates how much that the part actually offers. In the TO263 package, for example, we have a clearance distance of 7.3 millimeters, and we have a creepage distance of about 6.9 millimeters, which should be enough to handle your industrial applications. The TO220 package, for example, the clearance distance between the pins on that is only 2.34 millimeters compared to this TO263 with its more than 7 millimeters between the pins and the drain tab. The TO263 is definitely the package to go with if you're dealing with this high voltage and are concerned with creepage and clearance.
So, Mitch, what is the maximum AC input voltage this kit can accept?
This kit can run from 480 volts three phase, which in the United States is typically the most voltage that you will run into in your industrial applications, unless you are in a major manufacturing operation. 483 phase is probably one of the most popular mains input voltages for industry.
So, what about an integrated 1700 volt silicon carbide MOSFET converter? Can you talk about that ROHM solution as well?
That's basically the family of parts that we've been discussing, and I should mention that those are also available with either auto restart from an overload or auto restart from over voltage, like some of the controllers we talked about before. So you just choose the appropriate part number for the type of restart operation that you are interested in.
Okay, so what about a silicon carbide controller IC? Does ROHM offer this kind of solution as well?
Yes, we do. The silicon carbide controller is the BD768X FJ-LB, and it's in the SOP J8 package. And it is a quasi-resonant controller, so we expect low EMI from this product. It draws a very low current consumption during standby on the order of 19 microamps, and this particular one operates at 120 kilohertz. It has a cycle by cycle overcurrent protection. It's a very good match with a silicon carbide MOSFET. We have a big selection of 650 volt, 750 volt, 1200 volt, and even a single part that's a 1700 volt MOSFET. So you can pair this up with the external MOSFET if you want a separate solution rather than an integrated solution. It's a little less expensive by going with the separate controller and a discrete MOSFET than what the integrated solution is. If you've got the real estate to handle these two separate parts, then it is a little less expensive way to go. This just shows a nice picture of the silicon carbide evaluation kit and shows the efficiency with DC input voltages of 300, 600, and 900 volts.
So, you also mentioned AC to DC controllers with external MOSFETs earlier. Can we also look at these solutions?
Sure. So these solutions run at typically 65 kilohertz. This would be our BD7672, BD7673, and BD7679 solutions. They run at 65 kilohertz and they run in traditional PWM current mode control. So they're not the quasi resonant like some of the other parts we talked about. They're going to have a little more EMI than the quasi-resonant parts, but in general, they're priced a little less costly. So they do have the jitter function on the 65 kilohertz. So that's a plus or minus 4 kilohertz approximately, a purposeful jitter that tends to spread the EMI over a broader spectrum and reduce the height of the peaks of the EMI. And they do have cycle by cycle overcurrent protection and a soft start feature. Coming in the SSOP6 package, they are one of our smallest solutions. And like many of our other solutions, you can get them with auto restart for fault or latch on fault to where you have to disconnect the primary voltage to get out of the fault condition.
So, Mitch, what about standard AC to DC controllers? What kind of options does ROHM offer here?
So that would be our BM1P, 061, 062, 101, and 102 family. Those families operate at either 65 kilohertz or 100 kilohertz, and they have a 650-volt starter inside of them. So that gets the chip up and running when you first connect mains power to the system. And they also have the frequency hopping function like the other chips we talked about. They do have a feature that can detect if there are some faults on the circuit board, CS pin open protection. And so if the current sensing pin becomes open for whatever reason, then you don't have a catastrophic failure. They will shut down to prevent damaging your power device on account of that. They do come in that family of choice of failure mode, like the others, where they have automatic restart after detecting an over voltage condition, or a latch condition where they stay off until the mains power becomes disconnected. We've got 4 parts, each with their own behavior for fault condition and your choice of 2 different switching frequencies.
So, what about AC to DC controllers with an X cap discharge? What does ROHM offer here?
So I think our simplest part that offers that X-cap discharge would be our BM1P10 CFJ family. And this also has the ability to control the minimum on time as well to improve the light load efficiency. And it also has low voltage protection for incoming AC. So you won't continue to try to operate the part in the event of a brownout. It will shut down rather than cause damage. So in the light load mode, this can be set up with a minimum on time as low as 2 microseconds. And for some applications that need a small part and you can benefit from the X cap discharge, this is a good fit. So this is just showing some of the benefits of this part. This BM1P10 has got the ability to adjust where it declares overcurrent based on the input voltage. So basically, it is set up to let you extract a certain amount of power from your power supply. Of course, as the input voltage becomes higher, for the same amount of power, the input current should go down. So what this does is it adjusts its current limit based on the amount of input voltage. So you end up getting the same amount of power out of the part, whether the input voltage is high or low. It can be set up with a resistor to set up that minimum on time to improve efficiency at light load. We say that it's almost lossless switching at light load because the on time of 2 microseconds is so small.
So, this solution has a peak power mode as well, right? So, talk to me about that aspect of the solution.
Yes, in some cases, the load tends to need a large amount of power for a short time, like a few milliseconds to get a motor up to speed or something like that. So, this particular BM1P10 can adjust itself to allow you to have more current than normal for anywhere from maybe half a second up to a little over 1 second. It will let you draw more current than normal to get that motor up to speed. And then after that, it will back down to the normal amount of power. If you happen to be lighting an incandescent bulb, for example, that's another case where for a few hundred milliseconds, you need more current than normal. And then after the bulb becomes lit and the filament is a higher resistance, the amount of power you need goes down significantly. If that's the nature of your load, is that it does need high peak power at the beginning, then that BM1P10 is a good part to look at. So we do have an evaluation board for the BM1P10, and the evaluation board is set up to deliver 24 volts at 2 amps, and we do have curves available in the guide for the board that show output current versus efficiency, show load regulation, output current versus output voltage, line regulation, the input voltage versus output voltage. So it's a well-documented evaluation kit for that BM1P product.
Excellent. Well, Mitch, I think that's all I have time for today. Thank you so much for joining me.
Thank you, Amelia. My pleasure.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from ROHM Semiconductor. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.